What if the object designated 3I Atlas turns out to be a truly extraordinary event, a cosmic anomaly so rare it reshapes the course of history? Initially, it was classified as just another celestial nomad, a frozen remnant from an unknown corner of space, drifting serenely past our sun, leaving behind only traces of data and faint dust trails. However, it did not continue on its solitary path. Instead, it began to accelerate, not with the random fluctuations of natural forces, but with a deliberate intent. Its velocity shifted, its luminosity pulsed rhythmically, suggesting an unseen hand was guiding its course. This is where conventional physics faltered. The established equations crumbled. What was once predictable became unfathomable. While the scientific community labels it an anomaly, could it signify something far more profound? Could this be a one-in-a-billion occurrence? A moment that fundamentally alters our comprehension of gravity, the passage of time, and the very nature of chance. Remain vigilant, for tonight you will grasp why an event of such immense rarity, perhaps never to be repeated in our planet's existence, might be unfolding before our eyes. If this enigma has captivated you as much as it has me, please show your support by hitting the like button and subscribing to ensure you receive every update as this situation develops in real time. Share your thoughts in the comments. Where are you watching from? What time is it in your location? And what are your initial impressions of this developing scenario? To aid in the expansion of this community, kindly share this video across X, Facebook, Reddit, or even within your personal messaging groups. Your engagement is the driving force behind our ability to uncover and present such remarkable stories. Therefore, we extend our sincere gratitude for your unwavering support. Part 1. Unveiling the latest anomalies. Picture this: observatories worldwide, their sophisticated instruments aligning in perfect synchronization. Complex orbital projections flicker across screens within the hushed confines of dimly lit control rooms. Suddenly, a dramatic eruption of water vapor emanates from a frigid celestial body millions of miles from the sun. News feeds erupt with sensational headlines: alien technology, unexpected acceleration, a phenomenon never before witnessed. This is not a figment of science fiction. It is a present-day reality, and it has a designation: 3I Atlas. This interstellar comet, first detected in July of 2025, was expected to behave like countless other icy, rocky fragments we have catalogued: predictable, measurable, and harmless. Yet, 3I Atlas defies these expectations. The more we scrutinize it, the more enigmatic it becomes. When astronomers first identified this visitor from beyond our solar system, their expectations were based on the established behavior of similar objects, such as the predecessor, Oumuamua. They anticipated typical cometary activity: outgassing, increasing brightness as it neared the sun, and a trajectory subtly altered by plumes of vaporizing ice. Nothing alarming, nothing to cause undue concern. However, within weeks of its discovery, the gathered data began to deviate significantly from these predictions. Now, months later, we are confronted with a situation that defies conventional understanding. Consider this detail, which should send a shiver down your spine. This comet is expelling water at an astonishing rate, akin to a fire hose. And remarkably, this activity is not occurring near the sun, where solar radiation would typically vaporize frozen volatiles. Instead, it is happening at an approximate distance of 2.9 astronomical units from the sun, nearly 3 times the distance between Earth and our star. At such a remove, most comets remain dormant, inactive, and thoroughly frozen, but 3I Atlas is remarkably active, exhibiting an intensity that scientists are struggling to explain. The James Webb Space Telescope, with its powerful infrared capabilities, turned its gaze upon this object and detected an even more perplexing characteristic. The coma, the luminous envelope of gas and dust surrounding the comet's nucleus, is predominantly composed of carbon dioxide, not water. The ratio of carbon dioxide to water is approximately 8:1, signifying one of the highest carbon dioxide to water proportions ever observed in a comet throughout the entire history of cometary science. Reflect on this. We have meticulously studied hundreds of comets, analyzed their chemical makeup, and developed extensive models. Then this entity arrives from interstellar space and fundamentally disrupts our established patterns. This presents a central dilemma. If this is indeed a comet, a naturally occurring celestial body composed of ice and rock, why is it so extraordinarily active so far from the Sun? Why does its chemical composition exhibit such extreme characteristics? And if its nature is not entirely natural, if there exists even the slightest possibility that it is something else, then what are the implications? A growing number of astronomers are cautiously beginning to use a term typically associated with financial markets and epidemiological studies, a Black Swan event. This refers to an occurrence so rare and unpredictable that it redefines established frameworks after it has transpired. I understand your potential skepticism. Comets are known for their peculiarities, and space is replete with outliers. However, consider this. Astrophysicist Avi Loeb, the same scientist who posited that Oumuamua might have been an artificial construct, has highlighted that 3I Atlas displays non-gravitational acceleration anomalies that do not align with conventional models. When a comet releases gas, these jets exert a push that slightly alters its trajectory. This is a standard and anticipated phenomenon. However, 3I Atlas is not accelerating in the manner predicted by these models. Alternatively, it might be accelerating, but the magnitude of the forces involved does not correspond to the observed rates of gas expulsion. Regardless, a fundamental discrepancy exists. When fundamental principles of physics appear not to add up, it compels us to pose difficult questions. Let me illustrate its trajectory. This object is traversing a hyperbolic orbit, indicating its origin from interstellar space and its eventual departure from our solar system, never to return. It is moving in a retrograde direction, meaning it orbits the Sun in opposition to the planetary orbits. Its inclination relative to the ecliptic, the plane containing most planetary orbits, is a mere 5 degrees. While this may not seem significant, it is statistically unusual. Most interstellar objects are expected to arrive from random angles, yet this one entered our solar system almost perfectly aligned with our planetary disk, as if it had a precise destination in mind. Its closest approach to the Sun, known as perihelion, occurred on October 29, 2025, only a few days ago. At this very moment as you are listening, 3I Atlas is arcing around the Sun and commencing its outward journey, while scientists are working feverishly to collect every available piece of data before it recedes into the cosmic background. But here is the question that should occupy your thoughts tonight. Could this object precipitate a chain reaction of unexpected events? Could it already be challenging our fundamental assumptions about what is possible? Could it be the initial domino in a sequence we have yet to even conceive? Because if 3I Atlas truly is a Black Swan event, then by definition, we will only recognize its significance after its consequences have fully manifested. Over the next 2 hours, we will investigate whether 3I Atlas is simply an exceptionally peculiar object, a statistical outlier within an immeasurably vast universe, or if it is subtly yet definitively rewriting the fundamental laws of space. We will explore 8 distinct scenarios ranging from the highly probable to the wildly speculative. Some of these scenarios are firmly rooted in the principles of orbital mechanics and observational astronomy. Others venture into territory that will undoubtedly provoke skepticism, but that is precisely the nature of a Black Swan event. Such an event is not intended to be obvious. It is designed to remain concealed until the precise moment it irrevocably alters everything. We will examine potential orbital perturbations that could trigger cascading effects for decades to come. We will consider fragmentation events that might pose future threats. We will contemplate whether this comet could interact with the Sun in unprecedented ways. We will investigate the possibility of artificial signals masked within ambient noise. We will explore atmospheric anomalies, cascading disclosures of information, profound psychological impacts, and even glitches in reality itself. Moments where the instrumentation might reveal subtle cracks in our understanding of time and space. And here lies a sobering truth. We may already be immersed within this Black Swan event. We might be observing its unfolding in real time, misinterpreting its significance as mere scientific curiosity rather than a potential catastrophe. For this is the inherent nature of such events. Their true meaning only becomes apparent in retrospect, after the paradigm has shifted, after the rules have been rewritten, and when it is too late to implement any form of preparation. Therefore, let us commence. Let us peel back the layers. Let us scrutinize the data, the speculation, the apprehension, and the wonder. Let us dare to ask the question that many are reluctant to voice aloud. What if Atlas is not merely passing through? What if it represents the harbinger of something we are not yet equipped to name? Part 2. Observed deviations from expectation. Before we delve into the specifics of these anomalies, it is crucial to establish a baseline understanding. We need to clearly define what constitutes normal behavior, because the only way to identify a deviation is by knowing the standard from which it departs. In the context of interstellar comets, we actually possess a reasonably comprehensive understanding of typical characteristics, or at least we believed we did. As a comet approaches the Sun, solar radiation warms its surface. The ice then sublimates, transitioning directly from a solid state to a gaseous one. This gas escapes through fissures and vents in the comet's nucleus, carrying entrained dust particles along with it. This process gives rise to the coma, the luminous atmosphere, and occasionally a tail that can extend for millions of miles behind the comet. Furthermore, the jets of gas function as miniature thrusters, subtly nudging the comet off its purely gravitational trajectory. This phenomenon is termed non-gravitational acceleration, and it is inherently predictable. Based on the comet's distance from the Sun, its size, and its composition, astronomers are able to calculate the extent to which it will deviate from a path dictated solely by gravity. Comets also exhibit increasing brightness as they approach the Sun. This brightening follows a power law relationship. The closer they get, the more active they become, and consequently, the brighter they appear. Scientists employ a metric known as the heliocentric distance exponent to characterize this relationship. For the majority of comets, this exponent falls within a specific range. If it deviates significantly higher or lower, it suggests an unusual composition or behavioral pattern. Thus, that is our established baseline. Outgassing intensifies closer to the Sun. Brightness follows predictable curves. Non-gravitational forces are commensurate with outgassing rates, and photometric behavior aligns with solar distance. These are simple, testable, and reliable principles. Now let us address 3I Atlas. At an approximate distance of 2.9 astronomical units from the Sun, it was already exhibiting water expulsion rates typically observed much nearer to the Sun. Imagine activating a faucet in a deep freeze and having water gush out regardless. That is essentially the scenario unfolding here. At this distance, most comets are quiescent, their surfaces far too cold to facilitate substantial sublimation. Yet, this comet appears unfazed by our established models. The James Webb Space Telescope's analysis of its coma's composition revealed something extraordinary. Carbon dioxide is the dominant component. The ratio of carbon dioxide to water is approximately 8:1. To provide context, most comets within our solar system exhibit ratios closer to 1:10 or 1:20, with water typically being the most prevalent volatile substance. Here, however, carbon dioxide reigns supreme, and the reason remains elusive. Is the nucleus unusually rich in carbon dioxide ice? Did it originate in a colder, more carbon-abundant region of its parent star system? Or is some other process releasing the carbon dioxide in a manner we do not yet comprehend? Dust production presents another anomaly. Observations conducted by the Nordic Optical Telescope measured how dust production scales with distance. The power law index derived from these measurements was approximately 3.8, with a margin of error of 0.3. This figure indicates the comet's sensitivity to solar heating. A higher index signifies rapid changes in activity, while a lower index suggests more gradual alterations. 3I Atlas falls within a recognized range, but it is situated at the upper end of that spectrum, reacting to solar radiation with a vigor exceeding what would be anticipated for an object of its presumed composition. Furthermore, there is the matter of polarimetry. When sunlight reflects off dust particles within the coma, it becomes polarized. The degree and angle of this polarization are contingent upon the size, shape, and composition of the dust grains. Astronomers who observed 3I Atlas reported what they termed extreme negative polarization, a complex way of stating that the polarization characteristics do not align with those of known solar system comets. The dependence of polarization on the phase angle, meaning how polarization shifts with variations in the viewing angle, is also unusual, distinct, and anomalous. Now let us consider its trajectory. 3I Atlas is following a hyperbolic orbit with an eccentricity exceeding 1. This confirms that it is not gravitationally bound to the Sun and will eventually escape its influence. Its inclination relative to the ecliptic is approximately 5 degrees, and it is moving retrograde. This combination of orbital parameters is statistically uncommon. The majority of interstellar objects are expected to arrive from random directions. The fact that this particular object entered our solar system in such close alignment with the plane of the planets is, at best, a remarkable coincidence. Perhaps. But in astronomy, Coincidences often serve as indicators of deeper underlying truths. Perihelion, the closest approach to the Sun, occurred on October 29, 2025. Currently, the comet is moving outbound. On October 3, 2025, it passed within approximately 0.19 astronomical units of Mars. This is a close proximity, closer than many encounters with near-Earth asteroids. On November 3rd, it will pass within 0.65 astronomical units of Venus, and in March of 2026, it will approach within 0.36 astronomical units of Jupiter. While these close approaches do not pose a risk of collision, they do raise pertinent questions regarding gravitational interactions. Could this object potentially perturb the orbits of smaller celestial bodies? Could it subtly alter the trajectory of an asteroid? We will revisit this critical question later. This is where the situation becomes truly perplexing. Despite significant outgassing and the continuous expulsion of water and carbon dioxide from its surface, 3I Atlas is not exhibiting the predicted non-gravitational acceleration. Or more accurately, the acceleration observed is considerably weaker than what theoretical models suggest. Avi Loeb has pointed out that this implies the nucleus must possess a substantial mass or an exceptionally high density. If the outward jets are propelling a massive object, the resulting acceleration would naturally be minimal. However, if the nucleus is small and the outgassing is minimal, then where is all this expelled water originating from? The numbers simply do not reconcile. The forces involved do not appear to be in balance. There is a crucial element missing from the equation. Estimates of the nucleus's size vary considerably. Depending on the assumptions made regarding reflectivity and composition, the nucleus could range anywhere from 0.32 kilometers to 5.6 kilometers in diameter. This represents a vast degree of uncertainty, and this uncertainty propagates through every subsequent calculation. If the nucleus is small, the observed outgassing rates become absurd. Conversely, if it is large, the lack of corresponding acceleration becomes equally absurd. In either scenario, we are confronted with an absurdity. Therefore, what can we infer from this? If outgassing is expected to alter the object's trajectory, yet it deviates only minimally, we are left with a few possible explanations. Perhaps the expulsion jets are perfectly symmetrical, effectively canceling each other out. Alternatively, the nucleus might be rotating in such a way that distributes the thrust evenly. It is also conceivable that the ejected material is moving at such a slow velocity that it imparts negligible momentum. Or perhaps, just perhaps, the nucleus is composed of a material far denser than anything we have encountered before. Denser than rock, denser than iron, dense enough to prompt speculation about its very composition. And this brings us to the uncomfortable question: is this merely an exceptionally unusual comet, or is it the initial indicator of something far more unpredictable? Because if we are unable to explain its behavior using standard scientific models, then our models are by definition incomplete. And if our models are incomplete, what other crucial aspects of this phenomenon might we have overlooked? Part 3. Media and community reaction. Speculative framing. The astronomical community finds itself divided. On one side stand the adherents of scientific rigor, the researchers who have dedicated their careers to studying comets, individuals who place their faith in empirical data, await peer review, and consciously resist sensationalism. On the other side are the provocateurs, researchers willing to entertain hypotheses with low probabilities but potentially significant impacts, individuals who believe the universe may still harbor profound surprises. Navigating this divide, the media amplifies both perspectives, sometimes with commendable responsibility, and at other times with reckless abandon. Tom Statler, NASA's lead scientist for small bodies in the solar system, has publicly stated that 3I Atlas exhibits characteristics consistent with a comet. He has emphasized that the overwhelming body of evidence points towards a natural celestial object, citing water outgassing, dust production, and photometric behavior that aligns with sublimation processes, all hallmarks of a comet with no indication of anything artificial or exotic. He posits it is simply a chunk of ice from another star system, behaving as such objects typically do. However, there is also Avi Loeb, the Harvard astronomer, who gained widespread recognition for suggesting that Oumuamua might have been a light sail. Loeb has been a vocal proponent of considering exotic explanations for 3I Atlas. He has drawn attention to the observed acceleration anomalies and has questioned the underlying assumptions of our scientific models. He urges the scientific community not to dismiss low-probability hypotheses without thorough investigation. He is not asserting it is alien in origin. Rather, he advocates for exploration because without it, the truth will remain unknown. The media's portrayal has been varied. Tabloids have splashed headlines concerning disguised hostile alien technology. Major news outlets have embraced the Black Swan framing, describing it as a rare object with the potential to redefine our understanding of everything. The Guardian has published articles that skillfully balance scientific caution with public fascination. Live Science has explored the possibility of artificial origins, framing it as improbable, but not entirely impossible. EFL Science has covered Loeb's statements, underscoring the critical importance of disproving exotic explanations through empirical observation rather than preconceived assumptions. The Times of India has labeled 3I Atlas a rare black swan object and has referenced an international observation campaign coordinated by the International Asteroid Warning Network, IAWN, a consortium of telescopes and space agencies dedicated to the detection and tracking of near-Earth objects. The involvement of such an organization suggests that this object is being taken seriously, not as an immediate threat but as something meriting close scrutiny. So, why would scientists entertain narratives of alien technology at all? Why risk their professional credibility by engaging with speculative hypotheses? The answer lies in the asymmetry of the stakes. If one dismisses a low-probability event and it subsequently proves to be real, the repercussions can be catastrophic. Conversely, if one investigates an unlikely scenario and finds no conclusive evidence, the primary cost is the expenditure of time and resources. This reflects the logic of Pascal's wager applied to the field of astronomy. The potential cost of being wrong outweighs the perceived cost of appearing foolish. However, there exists a more concerning dimension to this discourse. Speculation invariably breeds fear. It attracts individuals predisposed to conspiracy theories. It erodes the distinction between responsible scientific inquiry and irresponsible fear-mongering. When mainstream media outlets employ phrases such as alien technology and black swan, they are not merely reporting events. They are actively shaping public perception. They are influencing how the public and even policymakers react to uncertainty. Consider this scenario. What if 3I Atlas is entirely benign? What if it is merely a comet with unusual yet ultimately explainable chemical properties? However, due to the prevailing speculation and the narrative framing, resources might be diverted. Telescopes could be redirected from other scientific targets to focus on this object. Discussions about planetary defense budgets might be initiated. International collaborative efforts might be formed around a non-existent threat. All of this could transpire simply because we failed to differentiate between prudent caution and unwarranted paranoia. On the other hand, what if the speculation is entirely justified? What if there is even a 1% probability that this object represents something unprecedented? In such a case, ignoring it would constitute negligence, a potentially dangerous oversight, and a failure of both imagination and duty. For the fundamental characteristic of a black swan event is its unpredictability. One cannot adequately prepare for it by adhering to established protocols. It demands a willingness to consider the seemingly impossible. This inherent tension influences funding allocations, the distribution of telescope observation time, and the level of seriousness with which space agencies approach follow-up investigations. If an object is labeled a mere curiosity, it receives minimal attention. However, if it is designated as a potential black swan, it instantly garners widespread interest. Careers can be forged or broken based on whether the accompanying hype proves to be validated. Furthermore, there is a significant psychological dimension to this phenomenon. Why are people so intensely fascinated by this particular event? Why does the concept of an interstellar visitor evoke both profound wonder and deep-seated dread? Perhaps it serves as a stark reminder of our own cosmic insignificance, the fragility of our current understanding, and the vast expanse of the unknown that still characterizes our universe. Or perhaps deep down, we are yearning for something to disrupt the mundane, a definitive proof that we are not alone. Or conversely, evidence that the cosmos is far stranger than we could have ever imagined. The concept of a black swan is not solely scientific. It is also cultural, reflecting how we respond to the unknown. Do we dismiss it as mere background noise? Do we meticulously investigate it as a significant signal? Do we allow fear to dictate our actions, or do we embrace curiosity? Because once a black swan event has occurred, once the fundamental paradigm has shifted, there is no turning back. The new reality cannot be unseen, and the knowledge gained cannot be forgotten. The world is irrevocably altered in its aftermath. Therefore, the crucial question remains: are we artificially inflating 3i Atlas into something it is not? Or are we finally giving serious consideration to the possibility that the vastness of space still holds the capacity to surprise us? Because the answer to this question will ultimately shape our response to the next anomaly, and the one that follows, and the one after that. To determine if this is mere sensationalism or a genuine hazard, we must first establish what a celestial Black Swan event would entail. Without a defining framework, without specific criteria, our speculation remains unfettered, and mere conjecture is insufficient, especially given the potential gravity of the situation. Part 4 delves into defining what a space-based black swan could be. The term black swan originates with philosopher and statistician Nassim Taleb, who used it to characterize events that are infrequent, unpredictable, and possess profound repercussions. These are occurrences that, in retrospect, seem obvious, yet were entirely unforeseen beforehand. The archetypal illustration is the financial crisis of 2008. Experts had assured everyone of the system's stability, the diversification of risk, and manageable leverage, only for the system to collapse. Afterward, the warning signs were readily apparent. However, prior to the collapse, these signs were dismissed as inconsequential. Taleb posited that black swan events share three distinguishing features. Firstly, they lie beyond the scope of ordinary expectations. Nothing in past experience can credibly suggest their possibility. Secondly, they exert an extreme impact, transforming industries, societies, or even global perspectives. Thirdly, despite their unpredictability, human nature compels us to fabricate explanations post-event, rendering them seemingly comprehensible and foreseeable. We retroactively impose causality, stating that we should have anticipated them, when in reality, we could not have. So how do we translate this concept to astronomy? What would qualify as a black swan in the cosmic realm? Perhaps a comet that precipitates a chain reaction of orbital disturbances, or an object that unveils unknown physical principles, a signal that confirms extraterrestrial intelligence, a disruption so subtle that its true nature becomes evident only after decades have passed. Allow me to propose a preliminary set of criteria. A space black swan must exhibit at least three of the following attributes. Firstly, unpredictability that exceeds current theoretical models, not merely unusual or rare, but genuinely outside the parameters of existing scientific understanding. Secondly, a significant potential impact on planetary safety, on our scientific comprehension, on detection capabilities, or on humanity's perception of its cosmic standing. Thirdly, consequences that are irreversible, such as persistent orbital shifts spanning millennia, irreparable data corruption, or new discoveries that render established scientific texts obsolete. Fourthly, evidence suggesting intentionality or physical anomalies that transcend natural randomness. A signal inexplicable by known astrophysical processes, a trajectory alteration defying inertia, or a temporal coincidence too precise to be accidental. Now let us apply these criteria to 3I Atlas. Does it already meet any of them? Well, its unpredictability stems from its behavior not perfectly aligning with existing models. However, the question remains, is it genuinely beyond current models or merely at their fringes? This is debatable. Does it possess a high potential impact? Scientifically, yes, it challenges our assumptions. However, practically, it poses no direct threat to Earth. Does it exhibit irreversible consequences? Not yet. And evidence of intentionality? None that we have detected thus far. Therefore, by these standards, 3I Atlas is not a black swan, at least not at this juncture. Nevertheless, it possesses the potential to become one. If it performs an unexpected action, fragments in an unusual manner, perturbs another celestial body, if we detect a signal, or if any of a dozen improbable scenarios unfold, then in retrospect, we will acknowledge it as a black swan all along. This is the inherent paradox. One cannot identify a black swan before its occurrence. One can only prepare for the possibility. One can only develop systems sufficiently resilient to unforeseen events. One can only foster a mindset that regards the improbable as worthy of thorough investigation. So, what are the specific scenarios? What are the precise ways 3I Atlas could evolve into a black swan? I have identified 8. Some are rooted in established physics, others are speculative, and some verge on the metaphysical. Yet each represents a distinct form of potential catastrophe, a different trajectory from curiosity to crisis. The initial scenario I term orbital domino. A minor gravitational influence initiates a cascade of orbital alterations affecting other objects. Perhaps 3I Atlas subtly perturbs an asteroid as it traverses near Mars. This asteroid's orbit shifts slightly. Over the course of decades, this change amplifies. Eventually, the asteroid's path intersects Earth's, and we remain unaware because we failed to track the initial perturbation. The second scenario is a fragmentation event. The comet disintegrates in an unexpected fashion. For instance, one fragment exhibits directed motion. It might decelerate contrary to the direction of its outgassing. It might display behavior suggesting internal structure, propulsion, or an unknown mechanism. The third scenario is solar disruption. A solar event, such as a coronal mass ejection or a flare, coincides with the comet's closest approach to the Sun in an uncanny manner. There might be a feedback loop. Perhaps the comet triggers the event. The timing might be too precise to be random. Consequently, satellites could fail, leading to a communications blackout. Or auroras could appear in locations where they are not typically observed. The fourth scenario is an artificial signal. Telescopes detect a narrow band pulse. It is too brief to confirm and too faint to repeat, buried within noise until the correct algorithm is applied. This then raises the question: do we disclose it? Do we investigate further? Or do we suppress it due to the potentially destabilizing implications? The fifth scenario is an atmospheric anomaly. The comet's passage triggers or coincides with unforeseen disturbances in Earth's upper atmosphere, such as ionospheric spikes, GPS signal delays, out-of-season auroras, or similar phenomena observed by Mars orbiters. These effects would be transient and subtle, yet measurable. The sixth scenario is a disclosure cascade. Unforeseen leaks, coordinated official statements, or data releases timed to coincide with the object's flyby. This might be entirely benign, a standard scientific coordination effort. Alternatively, it could signal the commencement of a controlled information release, a gradual disclosure intended to prepare the public for a more significant revelation. The seventh scenario is a psychological singularity. Widespread public attention creates a social ripple effect characterized by synchronicity, heightened anxiety, and a collective conviction that a momentous event is imminent. Because everyone believes it, decisions are made, policies are altered, funding is allocated, and careers are redirected. The object gains significance not due to its intrinsic nature, but due to our perception of its potential. The eighth scenario is a reality glitch. This is an extreme speculative scenario involving slight desynchronization of instrumentation, pulsar timing residuals, anomalies in spacecraft telemetry, or atomic clock drift, all aligning with the comet's transit, as if the object is disrupting space-time itself or exposing a flaw in our understanding of time. Each of these scenarios poses a distinct question. Could a fragment redirect an asteroid decades from now? Is it possible we have already recorded a signal that vanished before we recognized its significance? Could a comet interact with the Sun in ways we have never witnessed? Could public perception manifest as a self-fulfilling prophecy? Some of these possibilities are grounded in scientific reality. Orbital perturbations and fragmentation are observable phenomena. Others are more akin to cinematic narratives, bordering on paranoia. However, that is precisely the point. A Black Swan event is not expected to be the most probable outcome. It is intended to be the overlooked scenario, the one dismissed by everyone as too implausible until it becomes undeniable. In the subsequent sections, we will meticulously examine each scenario. We will ascertain which ones remain plausible given current data, which are definitively ruled out, which are fundamentally unknowable, and which might already be in progress without our awareness. Because if even one of these scenarios proves to be real, our comprehension of the cosmos will be irrevocably altered. Part 5 provides a preview of these scenarios, outlining 8 peculiar possibilities. Let us explore these scenarios individually, not in exhaustive detail at this stage, but sufficiently to grasp their essence and the weight of their potential implications. Each scenario represents a unique manner in which the universe could surprise us, and each carries consequences for which we are unprepared. Scenario 1. Orbital Domino. Imagine 3I Atlas passing in proximity to Mars on October 3, 2025. It does not collide with any object, but its gravitational field exerts a minute pull on a small asteroid, a barely perceptible tug. The asteroid's velocity shifts by a fraction of a meter per second. This appears insignificant. Indeed, it is insignificant in the present moment. However, orbital paths are inherently sensitive systems. Minor deviations can accumulate significantly over time. 10 years later, the asteroid's trajectory has drifted. 20 years later, it intersects another orbit. 30 years later, it is on a collision course with Earth. And we failed to connect these events because we did not monitor the initial perturbation. Could 3I Atlas precipitate such a cascade? Could it nudge an object onto a path that poses a future threat? The mathematical calculations suggest this is possible, albeit improbable. Scenario 2. Fragmentation Event. Comets are known to fragment routinely due to thermal stress, rotational forces, or inherent structural weaknesses. This is a common occurrence. However, what if a fragment behaves unusually? What if it decelerates when it should accelerate? What if it changes direction contrary to the force exerted by its outgassing jets? Envision astronomers detecting a secondary brightness surge weeks after the comet's closest approach to the Sun. They would likely assume it is a fragment. However, upon calculating its trajectory, the figures would not align. The fragment's momentum would not correlate with the expected ejection velocity. Its motion would suggest an external impetus or steering mechanism. Is this naturally possible? Perhaps, but it would imply internal structural complexities, voids, pressure differentials, or other factors we have yet to consider. Scenario 3. Solar disruption. The Sun is a highly active star, with coronal mass ejections and solar flares occurring regularly. But what if such an event coincides precisely with the comet's perihelion passage? What if the timing is exceptionally precise? What if the comet's trajectory aligns with a massive coronal mass ejection directed squarely at Earth? Satellites could malfunction, power grids might experience fluctuations, auroras could appear at the equator, and scientists would grapple with determining whether it is mere coincidence or a causal relationship. Could a comet instigate a solar event? Mainstream astrophysics suggests this is unlikely, given the comet's diminutive size relative to the Sun's immense mass. However, could there be a feedback mechanism? Could the comet's ionized coma interact with the Sun's magnetic field in an unforeseen manner? Could our understanding of such thresholds be inaccurate? Scenario 4. Artificial signal. Radio telescopes continuously scan the cosmos, collecting vast amounts of data, filtering out noise, and searching for patterns. But what if a signal has already been recorded and overlooked? What if 3I Atlas emitted a brief pulse during its closest approach to the Sun? What if it was positioned behind the Sun, rendering immediate Follow-up impossible. What if the signal was dismissed as mere interference? Imagine a researcher, years from now, processing archival data with a novel algorithm and discovering something remarkable. A narrow-band emission, structured, non-random, pointing back to this specific moment and this particular object. Would we disclose this finding? Would we accept its implications? Or would we conceal it due to the potentially perilous ramifications? Scenario 5. Atmospheric anomaly. Earth's ionosphere is sensitive to solar wind and cosmic rays, but it also reacts to charged particles emanating from comets. What if 3I Atlas's coma interacts with Earth's magnetosphere? What if GPS signals exhibit unusual delays? What if ionospheric monitoring stations detect surges in ion density? What if Mars orbiters observe transient auroras during the close approach on October 3rd? These phenomena would be subtle, easily disregarded. However, if multiple independent instruments detect such occurrences within the same temporal window, coincidence begins to suggest correlation. And correlation necessitates an explanation. Scenario 6. Disclosure cascade. The International Asteroid Warning Network publicly coordinated an observation campaign for 3I Atlas. This information is readily available. However, what if undisclosed meetings took place? What if space agencies discreetly shared data? What if previously archived anomalies were re-released during this period? Not as a result of a conspiracy, but because this object warranted a more thorough examination of older data. And what if this closer scrutiny revealed discrepancies? Minor timing deviations in spacecraft telemetry, unexplained trajectory shifts in other missions. Nothing conclusive, but sufficient to provoke questions, thereby initiating a cascade of inquiries. Scenario 7. Psychological singularity. This scenario is difficult to quantify objectively. It is not rooted in physics, but in perception. What if a sufficient number of individuals come to believe that something significant is about to happen? What if social media amplifies speculative narratives? What if policymakers begin to take these concerns seriously? What if emergency sessions are convened? What if funding priorities are shifted? The object acquires importance not due to its actual properties, but because of our collective belief in its potential significance. In a peculiar fashion, our conviction alters reality, not the physical reality of the object, but our societal reality. Decisions are made, careers are altered, and history takes a different course, all because we were unable to distinguish genuine signals from background noise. Scenario 8. Reality glitch. This is the most extraordinary scenario, venturing into territory few scientists are willing to explore. What if numerous independent sensors recorded temporal anomalies during the comet's passage? Pulsar timing residuals, atomic clock drift, spacecraft telemetry delays, all minute, all within typical noise margins, yet all synchronized with 3I Atlas's perihelion. What would be the implications? Could ionized dust particles affect signal propagation? Could charged particles interfere with time distribution systems? Or could this indicate something more profound? A flaw in our synchronization mechanisms? A distortion in space-time? Or a hint that our clocks are not measuring time as we understand it? Now let us be clear. The majority of these scenarios are highly improbable, some bordering on impossible. However, the focus is not on probability, but on consequence. A Black Swan event does not announce itself. It lies hidden in the tail of statistical distributions, concealed within the noise. It only becomes apparent in retrospect. Over the ensuing segments, we will investigate which of these scenarios are supported by evidence, which are testable, which are purely speculative, and which might already be unfolding without our knowledge. Because if we are currently experiencing a Black Swan event, the only recourse is to investigate and to persist in our investigation until the full picture becomes clear, or until it is too late. Part 6 delves into scenarios 1 and 2, orbital domino and fragmentation event. Let us begin with the most plausible scenarios, those grounded in established physics, which do not necessitate exotic hypotheses or conspiratorial thinking. If 3I Atlas is to surprise us, it is most likely to do so in a subtle, delayed manner, concealed within the intricacies of orbital mechanics. The orbital domino scenario is one that causes considerable concern among planetary defense scientists. This is not due to its likelihood, but because its consequences escalate over time, and by the time the problem is recognized, intervention becomes impossible. Here's how it operates. 3I Atlas traverses the inner solar system. As it approaches planets and substantial asteroids, its gravitational field exerts a minuscule influence, a force infinitesimally small, negligible in the short term. However, orbital paths are inherently chaotic systems, highly sensitive to initial conditions. A minor alteration in velocity can lead to a significant change in position over the course of decades. On October 3, 2025, 3I Atlas passed within approximately 0.19 astronomical units of Mars, a distance of roughly 28 million kilometers. For perspective, the Moon is merely 384,000 kilometers from Earth. Therefore, this was a relatively close encounter by astronomical standards. Did it perturb any objects? Almost certainly. Mars possesses two small moons, Phobos and Deimos, whose orbits are already unstable over geological timescales. An approaching object could impart a slight nudge. Would this be immediately apparent? Likely not. The changes would be subtle, but over years, these deviations would compound. Furthermore, Mars hosts a population of co-orbital asteroids, known as Trojans, which share its orbital path. These asteroids are gravitationally stabilized at Lagrange points by Mars. However, stability is a relative term. A perturbation could dislodge one of these asteroids from its Lagrange point, rendering its trajectory unpredictable. It could drift inward towards Earth, outward towards the asteroid belt, or enter a resonant interaction with Jupiter that amplifies its orbital eccentricity. Let's consider the numerical aspects. Assuming 3I Atlas possesses a mass of 10 to the power of 14 kilograms, roughly equivalent to that of a mountain or a small comet nucleus. Its gravitational influence at a distance of 0.22 astronomical units would be exceedingly minor. However, minuscule does not equate to zero. Gravitational force diminishes with the square of the distance but never truly vanishes. Every object in the solar system exerts a force on every other object, and these forces are cumulative. Now consider an asteroid with a semi-major axis of 2 astronomical units, situated in the main asteroid belt. Its orbital period is approximately 3 years. If 3I Atlas perturbs its velocity by a mere 1 millimeter per second, this appears insignificant. Yet, over 10 orbital periods, or 30 years, this 1 millimeter per second translates into a positional shift of hundreds of kilometers. And if that asteroid happens to be on a trajectory that could eventually intersect Earth's orbit, those hundreds of kilometers could be the critical difference between a near miss and an impact. Planetary defense systems meticulously track near-Earth asteroids, cataloging their orbits and predicting close approaches. However, they do not monitor every asteroid. Those too small or too dim elude detection. Crucially, they do not account for perturbations caused by interstellar visitors, as until the discovery of Oumuamua, such visitors were purely hypothetical. Now, they are a reality. And if they are real, they can indeed perturb orbits, necessitating their inclusion in our calculations. Therefore, the pertinent question is, could 3 Atlas have nudged an object into a future threat trajectory? The answer is, we do not know. We lack complete orbital data for every small body in the solar system. We lack the computational power to model every conceivable perturbation, and we lack the telescopic coverage to detect subtle changes in trajectories. The gaps in our knowledge are extensive, and it is within these voids that black swans tend to reside. Now let us address the fragmentation event. Comets fragment frequently. It is one of their most common behaviors. Thermal stress from solar heating causes the nucleus to fracture. Rotational forces generate centrifugal stress that pulls apart weakly bound material. Sublimation of volatile ices beneath the surface creates internal pressure that expels fragments. We have observed numerous cometary fragmentations. Shoemaker-Levy 9, famously, disintegrated into multiple pieces before impacting Jupiter in 1994. Comet Schwarzmann-Volkmann 3 has fragmented repeatedly over decades. Therefore, fragmentation itself is not anomalous. However, what if the manner of fragmentation is unusual? What if a fragment does not behave as predicted by physical laws? Imagine this scenario. 3I Atlas is actively outgassing, with jets emanating from its nucleus. These jets impart momentum. When a fragment separates, it should inherit the parent body's velocity, augmented by the ejection velocity from the breakup. We can calculate the expected outcome. We can predict the fragment's brightness, its trajectory, and its subsequent evolution. But what if a fragment deviates from these predictions in a way that cannot be explained by outgassing jets? This would be peculiar, though not necessarily impossible. It would necessitate invoking internal structural characteristics. Perhaps the fragment contains voids that channel gas in specific directions. Perhaps it tumbles in a manner that generates asymmetric thrust. Perhaps it is composed primarily of dust with minimal ice, resulting in weak, yet discernible, outgassing. Or perhaps it signifies something else entirely, a mechanism we have yet to comprehend, a propulsive effect embedded within the physics of cometary activity. Or, in its most extreme interpretation, perhaps it is not entirely a natural phenomenon. Perhaps there is an internal component directing its motion. I am not suggesting this is probable, but rather that if a fragment exhibited such behavior, we would be compelled to consider it. Has 3I Atlas fragmented? As of its perihelion passage on October 29, 2025, there were no confirmed reports of fragmentation. However, this does not preclude the possibility of future fragmentation. Comets frequently break apart during or after perihelion, when thermal stress is at its peak. Subsequent observations over the coming weeks will be crucial. If there's a sudden surge in brightness, if images display multiple distinct entities, or if the observed path exhibits unanticipated divergences, these would be indicators. The truly disquieting aspect lies here. Should a fragment demonstrate aberrant behavior, how would we go about its examination? Telescopes possess inherent limitations in resolving minute details. Spectroscopic analysis can ascertain material composition, but offers no insight into physical arrangement. Radar may reveal rotational velocities and surface characteristics, yet this is contingent upon the fragment being sufficiently proximate. Furthermore, if its course diverges from the Sun's proximity, it simultaneously moves away from our planet. Each passing day diminishes its luminosity, rendering it more challenging to observe. Eventually, it will fade into the vastness of the cosmic background, leaving us with incomplete data, analogous to the intended pun, insufficient measurements, and unresolved inquiries. Could a detached piece then contribute to future hazards? Might it enter an extended orbital path that brings it back centuries hence? Could it influence the trajectory of another celestial body? Might it contain information about the parent object's structure that will remain forever beyond our retrieval? To all of these possibilities, the answer is yes. Fragmentation is an inherently unpredictable phenomenon. It introduces novel variables into a system already characterized by its inherent chaos. And each new variable presents a potential avenue for unforeseen outcomes. Allow me to present a hypothetical timeline. Imagine a fragment detaching in November of 2025. It would be too faint for immediate detection. It would drift. Over the span of 5 years, its orbital parameters would evolve. By 2030, it would intersect the orbital path of a near-Earth asteroid. By 2040, that asteroid's orbit would experience a minor alteration. By 2060, the asteroid would be set on a collision course with a constellation of satellites, and the connection to 3I Atlas would be lost, obscured by the protracted and convoluted chain of causation, buried beneath layers of noise. This is the orbital domino effect. It is the scenario that keeps orbital dynamicists awake at night. While orbital mechanics are theoretically deterministic, their practical application becomes chaotic. Trajectories can be predicted with exceptional precision over brief intervals. However, over periods spanning decades or even centuries, infinitesimal uncertainties magnify into substantial deviations. And that which cannot be predicted cannot be prevented. So, what is the assessment of these two scenarios? Are they plausible? Yes. Are they probable? No. Do they represent the potential for Black Swan events? Absolutely. Because the impact is delayed, the causal links are obscured, and by the time the repercussions become apparent, the originating event is a matter of ancient history. We would possess no means of tracing it back, no way to state that this occurred due to 3I Atlas. It would simply be perceived as another asteroid, another fragmentation event, another perturbation, lost within the cacophony of our chaotic solar system. Yet, if our commitment to planetary defense is genuine, if our long-term survival is a serious consideration, we must acknowledge these potential outcomes. We must track celestial visitors not only during their transit, but also in their aftermath. We must model their gravitational influence on smaller bodies. We must diligently monitor for fragmentation and thoroughly characterize any resulting pieces. For the universe operates independently of our theoretical frameworks. It disregards our assumptions. It simply proceeds according to its own laws. And our recourse is either to adapt or to face the ensuing consequences. This concludes Part 7, addressing Scenarios 3 and 4. Solar disruption coupled with an artificial signal. We are now entering a realm that causes considerable discomfort for the majority of scientific professionals. This unease stems not from physical impossibility, but from the requirement of highly improbable coincidences, temporal alignments, and correlations that, while potentially random, appear too remarkably precise. Humans as a species are notoriously inept at evaluating the significance of coincidence. We perceive patterns where none exist. We infer causality from mere correlation. We construct narratives that resonate with perceived truth, even when they diverge from objective reality. Nevertheless, there are instances where coincidences are not arbitrary. Sometimes the timing is critically important, and occasionally the universe presents us with an unexpected challenge that necessitates a thorough examination. Let us therefore explore the concept of solar disruption. This hypothesis posits that 3I Atlas's passage near the Sun could coincide with, or even precipitate, solar activity that subsequently affects Earth. The Sun is an inherently chaotic system. Its surface churns with convective currents, and its magnetic field undergoes complex twisting and entanglement. Every 11 years, the magnetic field undergoes a polarity reversal, driving the solar cycle. During periods of solar maximum, sunspot activity escalates. Coronal mass ejections become more frequent. Solar flares erupt with energies comparable to billions of nuclear detonations. All of this energetic activity propels radiation and charged particles into space. When a coronal mass ejection impacts Earth, it compresses our magnetosphere. Charged particles are channeled along magnetic field lines towards the poles. Upon colliding with atmospheric atoms in the upper atmosphere, they generate auroras. If the coronal mass ejection is sufficiently potent, it can induce currents within electrical grids, leading to the failure of transformers. It can disrupt satellite operations. It can cause widespread radio blackouts. The Carrington event of 1859 stands as the most powerful solar storm documented in recorded history. Telegraph systems experienced ignition. Auroras were observed as far south as the equator. Should an event of comparable magnitude occur today, the resulting economic devastation could amount to trillions of dollars. Therefore, solar activity is a tangible and significant force, posing considerable risks and exhibiting unpredictability on shorter timescales. While we can forecast the solar cycle and predict general trends, we cannot precisely determine the moment of a coronal mass ejection's eruption or its intended trajectory. The system's inherent chaos is too profound. The pertinent question then arises: could a comet interact with the Sun in a manner that triggers or intensifies solar activity? The prevailing consensus in mainstream astrophysics is a resounding no. The comet's mass is insignificant in comparison to the Sun's, rendering its gravitational influence negligible. If it possesses a magnetic field at all, it is utterly trivial. There exists no scientifically plausible mechanism by which a comet could exert influence over the Sun. However, let us consider secondary effects. What about the comet's ionized coma? As 3I Atlas approached its perihelion, its outgassing produced a cloud of ionized gas and dust. This cloud is electrically conductive. Could it establish a coupling with the Sun's magnetic field? Could it initiate a feedback loop? Could it act as a catalyst for instabilities that were already developing within the Sun's corona? I am not suggesting this is probable. I am suggesting it is not demonstrably impossible. And should solar activity surge during the perihelion window, if a significant coronal mass ejection were to erupt on October 29th or 30th, and if Earth were to experience unusual auroral displays or satellite disruptions within that precise time frame, we would be compelled to question whether it was a mere coincidence. Let me verify. Were there any notable solar events in the vicinity of October 29, 2025? Any coronal mass ejections, solar flares, or geomagnetic storms? If such events occurred, the temporal alignment would be striking. Conversely, if none were recorded, this particular scenario would lose considerable credibility. However, the absence of an event does not render the scenario impossible. It merely signifies that it did not manifest on that particular occasion. The critical inquiry extends beyond whether it occurred. It encompasses whether it could occur and whether we would be capable of recognizing it if it did. Now let us transition to the concept of an artificial signal. This is the scenario that elicits eye rolls from skeptics and invites ridicule. However, it also carries the most profound implications. Because if it is genuine, if 3I Atlas represents something beyond a natural comet, then everything changes. The search for extraterrestrial intelligence, or SETI, has been meticulously scanning the cosmos for decades. Radio telescopes are attuned to narrowband signals, while optical telescopes search for laser pulses. Sophisticated algorithms are employed to sift through background noise, hunting for discernible patterns. To date, no definitive extraterrestrial signal has been identified. The enigmatic WOW signal of 1977 remains unexplained but unrepeated. Fast radio bursts have subsequently been attributed to astrophysical phenomena, likely originating from magnetars. Every candidate signal encountered either dissipates into noise or is eventually explained by natural processes. However, consider this crucial point. SETI operates under the assumption that signals, if they exist, will be continuous or repetitive. A civilization deliberately broadcasting would presumably desire to be detected. Such transmissions would likely persist for extended durations, targeted towards potentially habitable star systems, and utilizing frequencies capable of penetrating interstellar dust. All these considerations are logical if the objective is communication across vast interstellar distances. But what if the intention is not broad broadcasting? What if the purpose is transit? What if the entity is a probe, transmitting only during perihelion, when solar conjunction provides a veil of obscurity? What if its signal is deliberately designed to be ambiguous, weak enough to be dismissed as interference, brief enough to prevent confirmation, yet structured sufficiently to be noticed by an exceptionally vigilant observer, but only if such close scrutiny is applied? Envision 3I Atlas emitting a pulse on October 29th. A narrowband emission at 1.42 GHz, the hydrogen line, a classic SETI frequency, lasting for merely 3 seconds. The signal strength would barely exceed the background noise. Telescopes would record it, but the data would likely be classified as radio frequency interference, human-generated and terrestrial, subsequently filtered out by standard algorithms, and perhaps never revisited. Years later, an individual might process archival data through a novel machine learning algorithm. This algorithm, unburdened by human biases, would simply seek patterns, and it might discover one. A brief, structured pulse, demonstrably non-random, originating from the direction of 3I Atlas during its perihelion passage. By that time, however, the object would have journeyed beyond Jupiter, fading into the darkness, rendering any follow-up or confirmation impossible. Would such a discovery be publicly announced? Would it be published? Or would it be suppressed? Because the ramifications are inherently destabilizing. If genuine, if artificial, it would signify that humanity is not alone, that we have been visited, and that our initial recognition was flawed. This, in turn, would raise disquieting questions regarding the number of other signals we have overlooked, the extent to which we have disregarded other visitors, and the degree of our collective blindness. Conversely, if it proves to be an artifact, mere noise, its announcement would precipitate widespread panic, erode public trust in scientific endeavors, fuel conspiracy theories, and divert crucial resources from legitimate research. Consequently, the decision-making process becomes political rather than purely scientific. Do we disseminate the truth, risking societal upheaval, or do we withhold information, risking accusations of a cover-up? This is precisely why the artificial signal scenario is so fraught with difficulty. It transcends mere detection. It encompasses the critical aspect of response, and response is contingent upon belief, which in turn is predicated upon evidence. And in this particular case, the evidence may be ambiguous, incomplete, and open to diverse interpretations. It is within the realm of interpretation that objectivity often falters. Therefore, the fundamental question remains: if a signal were detected, would you desire to be informed? Even if it could not be definitively confirmed, even if there was a possibility of error. Because while ignorance may offer comfort and certainty may be reassuring, ambiguity is profoundly maddening, and at times ambiguity is all that is attainable. This brings us to Part 8, Scenarios 5 and 6, Atmospheric Anomaly and Disclosure Cascade. Let us shift our focus from the vastness of deep space to something closer to home, Earth's atmosphere, specifically the ionosphere. This is the tenuous layer situated between altitudes of 100 and 1,000 kilometers, where solar ultraviolet radiation ionizes atmospheric atoms, creating a plasma. This layer plays a critical role in radio communication, reflecting certain frequencies that enable signals to propagate beyond the horizon. It also impacts GPS functionality. Satellites transmit signals through the ionosphere to ground-based receivers. However, the ionized plasma introduces delays into these signals. The magnitude of this delay is directly proportional to the electron density. Consequently, GPS systems continuously monitor ionospheric conditions and apply corrections. The ionosphere is acutely sensitive to solar activity. When the sun emits a flare or a coronal mass ejection, the energetic charged particles interact with Earth's magnetic field, inducing disturbances. These disturbances manifest visibly as auroras. They also cause fluctuations in electron density, leading to diminished GPS accuracy and degraded radio communications. In extreme situations, satellites can sustain damage. However, the ionosphere is also susceptible to other phenomena, such as meteor showers. When Earth traverses a stream of debris, countless meteors disintegrate within the upper atmosphere. The vaporized material ionizes, forming transient layers of elevated electron density. These layers can reflect radio waves in unconventional ways and can induce brief disruptions in satellite signals. The central question emerges: could 3I Atlas affect Earth's ionosphere? Not through direct impact, as it was not destined to collide with our planet. However, consider its coma, the cloud of ionized gas and dust trailing behind it. Could this cloud have intersected Earth's magnetosphere? Could it have generated a transient disturbance? The answer hinges on geometrical alignment. 3I Atlas achieved its closest approach to Earth in late September and early October, at a distance of approximately 1.2 astronomical units, roughly 180 million kilometers. This distance is too great for direct interaction. However, The coma extends significantly beyond the nucleus, and the ion tail, propelled by the solar wind, can stretch for millions of kilometers. Could this tail have grazed Earth's magnetosphere? Could charged particles originating from the comet have been channeled down magnetic field lines? I lack specific data on this matter, and I am uncertain if ionospheric conditions were meticulously monitored during that particular temporal window. Nevertheless, if such monitoring was conducted, and if ground-based receivers or satellites registered anomalous spikes in electron density, or if GPS signals exhibited unusual delays, and if any of these observations correlated with the comet's passage, it would indeed be noteworthy. While not conclusive, it would certainly be intriguing. Furthermore, let us consider Mars. On October 3rd, 3I Atlas passed within 0.19 astronomical units of Mars, a considerably closer proximity than its approach to Earth. Mars is equipped with orbiters, rovers, and various scientific instruments. Could any of these have detected atmospheric effects? Mars possesses a tenuous atmosphere, but it does have an ionosphere and experiences auroras. These auroras are driven not by a global magnetic field like Earth's, but by localized magnetic crustal anomalies. If the comet's coma interacted with Mars's ionosphere, and if orbiters detected transient glows or ion density fluctuations, that would be a significant observation. Again, I do not possess this data. It is possible that the data exists, perhaps residing in an archive, awaiting analysis by a dedicated researcher. Alternatively, it is plausible that no one was actively observing because, after all, 3I Atlas is merely a comet, presumed to be inert and non-threatening. Consequently, instruments might not have been optimally positioned, or the data might not have been flagged as particularly interesting. The anomaly, if it exists, might be lost within background noise. This is the frustrating characteristic of Black Swan events, the inability to know where to look until after the occurrence. By that time, the opportune moment has passed, the data is archived, and attention has shifted elsewhere. Now let us discuss the scenario of a disclosure cascade. This scenario is less concerned with the physical sciences and more with the dissemination of information, focusing on how space agencies communicate, what information is shared publicly, and the inherent delays between observation and announcement. The International Asteroid Warning Network orchestrated an observational campaign for 3I Atlas. This is public knowledge, involving multiple telescopes across various nations sharing data. Such a level of coordination is standard practice for objects of interest and does not inherently imply conspiracy. Rather, it signifies scientific collaboration. However, the situation becomes more complex when this collaboration potentially uncovers something unexpected. Imagine that telescopes detect an anomaly. It might not be dramatic, nor definitively proof of anything specific, but it could be significant enough to warrant a more detailed examination of archived data. It could justify discrete meetings and initiate internal discussions regarding how to appropriately frame the findings. Consider this hypothetical situation. During the observation campaign, an individual notices a discrepancy in spacecraft telemetry. Perhaps a Mars orbiter records a slight timing offset during the close approach on October 3rd. The offset might fall within acceptable error margins, yet it persists and coincides with the comet's proximity. Subsequent investigation involves examining telemetry from other missions, revealing additional offsets. These are subtle and minor, yet they exhibit a correlation. Individually, None of these observations provide definitive proof, but collectively, they are peculiar. They are peculiar enough for a memorandum to be drafted, for a working group to be established, and for data to be re-released with updated calibrations. If one is attentive and actively seeking patterns, this cascade might become noticeable. I am not asserting that this specific sequence of events occurred. I am illustrating a plausible mechanism by which disclosure could unfold in the 21st century. Not through a dramatic press conference or the presentation of irrefutable evidence, but rather as a gradual dissemination of information, a series of minor revelations. Each revelation, viewed in isolation, would be plausible and explainable. However, collectively, they would form a discernible pattern. This pattern would suggest that something significant was observed, deliberated upon, and deemed important enough to warrant a re-evaluation of existing assumptions. The critical point here is that if such a cascade is indeed in progress, we are unlikely to recognize it in real time. Recognition would only occur in retrospect, when someone meticulously connects the disparate pieces of information, when the chronological sequence becomes clear, and when archived memos, data releases, and informal workshops are synthesized into a coherent narrative. The precise moment of disclosure will be impossible to pinpoint, as it was not a singular event but an ongoing process, and processes, by their nature, remain imperceptible until their completion. Therefore, the pertinent question is whether we are currently experiencing such a disclosure cascade. Are space agencies engaged in quiet coordination? Are historical anomalies being re-examined? Are closed-door meetings taking place? Perhaps, perhaps not. However, the very fact that we cannot ascertain this with certainty encapsulates the core issue. Black Swan events thrive in ambiguity, residing within the interstitial spaces between data and interpretation, between observation and announcement. And sometimes, by the time an announcement is made, the originating event has already transpired. This concludes Part 8, covering Scenarios 5 and 6. Now we delve into Part 9, Scenarios 7 and 8, Psychological Singularity and Reality Glitch. We are venturing into the most unconventional territory, exploring scenarios that have less to do with the fundamental laws of physics and more to do with perception consciousness and humanity's response to the unknown. Because the impact of an event is not always physical. It can be psychological and social, fundamentally altering the way belief shapes reality. Psychological singularity is the concept that collective human attention can generate consequences independent of the object of that attention itself. Consider historical parallels. During Halley's Comet's appearance in 1910, a segment of the population experienced widespread panic. Newspapers disseminated alarming reports about Earth passing through the comet's tail. Entrepreneurs capitalized on this fear by marketing Comet pills intended to provide protection against poisonous gases. In reality, there was no inherent danger. The comet's tail is so diffuse that it poses no threat. Nevertheless, the belief in impending danger triggered palpable social ramifications, including anxiety, irrational behavior, and market volatility. The event's significance stemmed not from its intrinsic nature, but from the collective human reaction to it. Another pertinent example is the Y2K bug, also known as the year 2000 problem. Computers utilized two-digit year designations, leading to concerns among programmers that systems would malfunction when the year transitioned from 99 to 0. Billions of dollars were invested in system remediation. Contingency plans were meticulously drafted, and some individuals even stockpiled essential supplies. However, as midnight struck, no catastrophic failures materialized. Most systems functioned as expected. Yet the preparatory measures, the widespread fear, and the collective response all had tangible consequences. Resources were reallocated, careers were advanced, and entire industries experienced shifts in focus. Now, what if 3I Atlas were to instigate a similar phenomenon? What if speculation began to proliferate? What if media coverage intensified exponentially? What if a critical mass of individuals started to believe that something significant was imminent, not due to concrete evidence but driven by the momentum of the narrative? Because the story felt intrinsically true, and because humans, finding uncertainty deeply uncomfortable, crave resolution. Imagine this scenario unfolding. Social media platforms erupt with myriad theories. Online forums become abuzz with discussions. Hashtags related to the Comet trend globally. Some individuals claim to have experienced prophetic dreams about the comet's arrival. Others report witnessing synchronistic events, meaningful coincidences seemingly tied to the specific date. Scientists issue carefully worded statements attempting to allay public fears, but their pronouncements are measured and cautious, often employing phrases like "no evidence of danger" rather than an absolute declaration of "absolutely safe." This linguistic hedging, this inherent caution, is frequently misinterpreted as doubt, as an indication of concealed knowledge, or as confirmation that vital information is being withheld. Policymakers begin receiving numerous calls. Journalists intensify their questioning. Congressional aides request urgent briefings. Consequently, space agencies find themselves compelled to respond. This response is not prompted by any actual threat posed by the comet, but rather by the escalating perception of threat, which has gained significant momentum. And this momentum, in turn, generates tangible, real-world consequences. Budgets are reevaluated, telescope observation time is reallocated, and emergency protocols undergo rigorous review. These actions are driven not by empirical data, but by prevailing belief. And here lies the recursive twist. Once these consequences materialize, once resources are diverted and the celestial object becomes the focal point of international attention, it acquires objective significance. Its importance is derived not from its inherent characteristics, but from what humanity has collectively made it. The belief system itself, in essence, creates the reality. The narrative becomes self-fulfilling. And years later, when historians examine this period, they will state that the 3I Atlas was of great importance, given everything that subsequently transpired. Consider the shifts in policy, the influx of funding. However, they will overlook the true origins of this importance, as it was not intrinsic but rather socially manufactured, engineered through pervasive collective apprehension. This represents a peculiar cognitive threshold, the juncture where curiosity eclipses comprehension, where conviction precedes substantiation, and the representation supersedes the reality. The most unsettling aspect is the impossibility of averting it, for any attempt to prevent it necessitates dialogue, and dialogue only serves to amplify the narrative. Absence of communication will be misconstrued as deliberate concealment. Openness will be perceived as validation. There is no triumphant strategy, only damage control. Now let us delve into the notion of a reality anomaly. This is a hypothetical situation that ventures into metaphysical realms, positing that the three-eye atlas could manifest or generate disruptions within the very framework of observation, affecting how we perceive time, the synchronization of our measuring devices, and the integrity of data streams. Contemporary astronomical pursuits rely on meticulous temporal accuracy. Spacecraft transmit signals that are precisely time-stamped. Pulsars emit regular emanations that function as cosmic chronometers. Terrestrial atomic clocks maintain synchronization with GPS satellites. All these systems operate under the fundamental assumption that time progresses uniformly, that clocks operate with predictable regularity, and that the universe adheres to a consistent chronological order. But what if there are unforeseen irregularities? What if, under particular circumstances, temporal synchronization systems become desynchronized? What if multiple independent instruments registered minor discrepancies within the same observational window? Offsets measured in microseconds, residuals in nanoseconds, all coinciding with the three-eye atlas's closest approach to the Sun. Is such a phenomenon physically conceivable? Perhaps. Ionized plasma can influence signal propagation. Charged particles can disrupt electronic components. Extreme gravitational fields can induce relativistic time dilation. Yet, the three-eye atlas does not present such extremes. Its mass is insignificant, its gravitational influence negligible. There appears to be no straightforward explanation for how it could impact timekeeping on Earth or within spacecraft, unless there is an element we are failing to apprehend. Unless the comet's coma generates an electromagnetic environment that subtly interacts with our instruments. Unless these temporal discrepancies are genuine and measurable, but fall below our detection thresholds until specifically investigated. Envision a scenario where a statistical analysis is conducted on pulsar timing data from October of the year 2025. The objective is to identify gravitational wave signals. Arrival times are cross-referenced across numerous observatories, and an anomaly is detected. A collection of residuals, small deviations from anticipated values, all occurring within the same week, the very week of perihelion. These deviations individually are within the acceptable margins of error and thus insignificant. However, collectively, they form a discernible pattern. Alternatively, consider spacecraft telemetry logs that exhibit timestamp anomalies. Orbital craft around Mars, probes near Jupiter, ground-based receiving stations, all recording signals that arrived marginally earlier or later than expected. Again, within the bounds of error tolerance but exhibiting correlation and synchronization, as if some influence was affecting signal transmission throughout the solar system during that precise interval. What would be the implications of such an event? Could it be an instrument malfunction? Certainly. Could it be a calibration error? Absolutely. Could it be random noise that by chance coalesces into a pattern? Yes. Or could it signify that our understanding of temporal measurement is incomplete? That there are environmental factors we have not yet accounted for? That an interstellar object traversing our immediate vicinity is creating disturbances beyond our current predictive capabilities? I am not asserting that this has occurred. I am exploring the potential ramifications if it were to happen. Because if temporal anomalies were indeed detected and found to be correlated with the three-eye atlas, it would be an extraordinary revelation. Not conclusive proof of artificiality, but evidence that the universe can still astound us. proof that our instruments, our theoretical frameworks, and our assumptions are not as infallible as we perceive them to be. And this is the essence of a Black Swan event. It is not about foreseeing the unforeseeable. It is about acknowledging the inherent existence of unpredictability, that systems possess a greater fragility than they appear to exhibit, that rare occurrences transpire with greater frequency than theoretical models suggest. And when they do, the repercussions can be irreversible. Therefore, which of these hypothetical scenarios holds true, which remain plausible, and which are definitively invalidated by forthcoming data, we are about to discover. For the narrative of the 3-Eye Atlas is still in its formative stages, and the sole method by which we can ascertain whether we are experiencing a Black Swan event is to maintain our vigilance, to continue our measurements, and to persistently question until the complete picture emerges or until it becomes irrelevant. Part 10. Cross-cutting mystery. What if it is already altering our comprehension? Let us pause and evaluate. We have examined 8 distinct scenarios. Some are rooted in principles of orbital mechanics, others are purely speculative, and some border on paranoia. However, it is now imperative that we organize these possibilities. We must assess their likelihood, their potential ramifications, and the extent to which any existing evidence supports them. Because without a structured framework, we are merely amassing fears, and fears, devoid of rigorous analysis, are ultimately futile. Thus, let us construct a simple table. Imagine it. For each scenario, we will assign a probability rating: low, medium, or high. We will evaluate the potential impact on scientific understanding, risk assessment, and paradigm shifts. And we will note whether any preliminary evidence exists, not definitive proof, but merely hints, observations that do not conclusively rule out the possibility. Orbital domino effect, plausibility, medium. We are aware that gravitational perturbations occur. We understand that orbits can become chaotic over extended periods. We know that the 3-Eye Atlas passed in proximity to Mars and is projected to approach Venus and Jupiter. Potential impact: high. A delayed chain reaction could precipitate future collisions decades hence. Evidence: none as yet. However, the absence of evidence does not equate to evidence of absence. The timescales involved are excessively long and the perturbations are exceedingly subtle. Fragmentation event, plausibility, medium. Comets are known to fragment with regularity. The occurrence of an anomalous fragment is not entirely inconceivable. Potential impact, medium to high, contingent upon the fragment's behavior. If it exhibits directed motion, that would represent a paradigm shift. Evidence: no confirmed fragmentation has been observed as of perihelion. However, follow-up observations are currently underway. Solar disruption, plausibility, low. There is no established mechanism by which a comet could instigate solar activity. Potential impact, high. A significant coronal mass ejection occurring during perihelion would profoundly affect Earth's infrastructure. Evidence: it would be necessary to review solar activity logs from late October of the year 2025. If a coronal mass ejection did occur, the temporal coincidence would be striking. Conversely, if none was observed, the credibility of this scenario would diminish. Artificial signal, plausibility, very low. This hypothesis necessitates extraordinary assumptions. Potential impact, extreme. It would confirm the existence of extraterrestrial intelligence and fundamentally rewrite human history. Evidence: none has been publicly acknowledged. However, it is possible that archival data has not been exhaustively analyzed with this specific hypothesis in mind. Atmospheric anomaly. Plausibility. Low to medium, depending on whether the comet's coma intersected Earth or Mars' magnetosphere. Potential impact. Low to medium. It would suggest the presence of unexpected particle interactions. Evidence. Unknown. This would require an examination of ionospheric monitoring data and Mars orbiter logs from early October. Disclosure cascade. Plausibility. Low to medium. Coordination among entities is commonplace. The existence of concealed anomalies would imply deliberate withholding of information. Potential impact. Medium. It would undermine trust in space agencies and suggest that prior discoveries were not fully disclosed. Evidence. Circumstantial. The IWN campaign is publicly accessible. Further investigation into other data releases would be necessary. Psychological singularity. Plausibility. Medium. Social dynamics are inherently unpredictable. Consequences driven by belief or historical fact. Potential impact. Medium. Real-world policy shifts, alterations in funding, and public anxiety. Evidence. Observable in media coverage and social media trends to some extent already. Reality. Glitch. Plausibility. Very low. This scenario requires the existence of unknown physics or systematic instrumentation errors. Potential impact. Extreme. It would challenge fundamental tenets of temporal measurement and signal propagation. Evidence. None exists. This would necessitate a comprehensive archival analysis of timing data from multiple independent sources. Consequently, what insights can we glean from this? The majority of these scenarios are improbable. Some possess plausible underlying mechanisms, but lack supporting evidence. A select few are already manifesting in subtle ways, such as the psychological singularity, and one or two, like the orbital domino effect and fragmentation, remain genuinely feasible over extended temporal scales. However, here lies the overarching question. If the 3I Atlas is sufficiently ordinary, if it is merely a comet exhibiting unusual yet explicable chemical properties, why does it continue to challenge the limits of our theoretical models? Why are scientists still engaged in debates regarding its behavior? Why are we entertaining such esoteric hypotheses at all? Perhaps our models are not as comprehensive as we once believed. Perhaps interstellar objects represent an entirely new domain, a novel parameter space where our ingrained assumptions falter. Perhaps the universe is reminding us that normal is merely a statistical construct, not an immutable law of nature. And if it is, in fact, abnormal, if it genuinely lies beyond our current predictive frameworks, do we possess the necessary systems in place to detect or respond to such an event? Planetary defense networks are equipped to monitor near-Earth asteroids, but they are not designed to track interstellar visitors. SETI actively listens for signals, but not from comets. Space agencies monitor solar activity, but they do not routinely correlate it with the passages of smaller celestial bodies. Our systems are compartmentalized, specialized, developed to address known threats, rather than unforeseen surprises. Therefore, should astronomers universally consider interstellar visitors as potential black swan candidates by default? Should every Oumuamua, every Borisov, every 3I Atlas be subjected to comprehensive observational scrutiny, including radio scans, infrared spectroscopy, radar, photometry, and trajectory monitoring for extended periods following their perihelion passage? Such an undertaking would be resource-intensive and necessitate significant interagency coordination. It would also mean diverting resources from other research priorities. But what is the cost of inaction? What is the cost of overlooking a crucial signal due to insufficient observation? What is the cost of disregarding a perturbation that could evolve into a significant threat decades in the future? The risk-reward trade-off is inherently unbalanced. The drawback of excessive caution is financial waste. The drawback of insufficient caution is potential catastrophe. And here lies the uncomfortable truth. We may already be participants within such an event. The Black Swan may have already commenced its subtle, gradual unfolding in ways that will only become apparent upon its completion. For this is the nature of such events. They do not announce their arrival. They do not await confirmation. They simply occur, and we subsequently scramble to comprehend their implications. Consequently, what are the critical decision points? What measurements retain their significance? Post-perihelion brightness evolution. Is its luminosity decaying as anticipated? Is there evidence of a secondary peak suggesting fragmentation? Updates on non-gravitational acceleration. Is the comet deviating from its predicted trajectory? Radio telescope follow-up. Has any effort been made to scan it for potential signals? Archival data sweeps. Are there any temporal anomalies present in spacecraft telemetry? Ionospheric monitoring. Were any disturbances detected during its close approaches? Each of these measurements represents a potential thread. Pulling a single thread might yield no significant result. However, by pulling a sufficient number of threads, a pattern might emerge. A pattern that was previously imperceptible. A pattern that could fundamentally alter our understanding. And this leads us to the concluding point. The 3-eye atlas is not the sole peculiar phenomenon gracing the celestial sphere. It is not the only anomaly that challenges our established assumptions. It is not the only object prompting scientists to pose uncomfortable questions. There are others. Fast radio bursts exhibiting inexplicable characteristics. Trans-Neptunian objects with unconventional orbital paths. Quantum experiments revealing temporal residuals, discoveries driven by artificial intelligence uncovering patterns that human observation had missed. The universe is replete with loose threads. And perhaps, just perhaps, they are all interwoven into the same grand tapestry. Part 11. Fast radio burst repeating oddities. Let us now shift our focus away from comets in the solar system, directing our gaze towards the vast expanse of deep space, where energetic radio pulses erupt from the darkness. Fast radio bursts, or FRBs, represent one of the most enigmatic phenomena in contemporary astrophysics, and in a peculiar manner, they may be linked to the ongoing narrative of the 3-eye atlas. Fast radio bursts, as their name suggests, are transient emissions of radio waves lasting mere milliseconds, possessing extraordinary intensity and detectable across billions of light years. The initial discovery occurred in 2001, embedded within archival data from the Parkes telescope, though its significance was not recognized until 2007. Since then, hundreds, perhaps even thousands, depending on the classification criteria, have been detected. The majority are singular events. They flash once and never repeat. However, a subset does exhibit repetition, and these repeating sources are particularly perplexing. Repetition implies a persistent origin, not a singular catastrophic event like a supernova, but rather a phenomenon capable of repeatedly emanating energy. This could be a neutron star, perhaps a magnetar with exceptionally strong magnetic fields, or something entirely novel. Something that has yet to be conceived. Allow me to present a recent example. FRB 22108A, discovered in the year 2022. This source repeats, but not randomly. It demonstrates periodicity, with bursts occurring in active windows, followed by periods of silence, and then recurring activity. This periodicity suggests rotation, possibly of a neutron star possessing a localized hotspot. Each time this hotspot rotates into our field of view, a burst is observed. This is the prevailing hypothesis. However, a significant challenge arises. The bursts do not perfectly align with established magnetar models. The frequency structure is anomalous. Some bursts display a sweep from high to low frequencies, while others do not. The polarization exhibits rotations that are difficult to reconcile with current theories. And the energy output is prodigious, equivalent to the sun's total energy production over decades, compressed into milliseconds. We are contemplating celestial objects comparable in size to cities unleashing unimaginable power. Are these phenomena natural? Almost certainly. Are they fully explained? No. And this is where the connection to the 3I Atlas becomes intriguing, as both entities challenge our established models. Both push the boundaries of our conventional understanding. Both invite speculation regarding exotic physics or even artificial origins. Consider this possibility. What if the 3I Atlas emitted a radio pulse during its perihelion passage? A brief, intense burst, powerful enough to be detected across galactic distances, yet strong enough to be intercepted by nearby radio telescopes, provided they were precisely oriented. What would be observed? A millisecond pulse, potentially exhibiting broadband or narrowband characteristics, perhaps with frequency modulation and polarization. Would we readily identify it as an FRB, or would we dismiss it as mere interference? The detection of FRBs is contingent upon our active search for them, the development of specialized detection algorithms, and continuous scanning of vast regions of the sky. However, comets are not typically targeted by radio telescopes in search of FRB-like emissions. Why would they be? Comets are essentially icy bodies. They do not generate the requisite magnetic fields for coherent radio emission, nor do they possess the necessary energy sources. They are typically considered passive objects that reflect and scatter solar radiation. Nothing more. But what if this assumption is fundamentally flawed? What if, under specific conditions, a comet's ionized coma can indeed generate radio emissions? What if the interaction between the solar wind and cometary plasma engenders instabilities, leading to magnetic reconnection events and coherent radiation? These are speculative notions, but they are not entirely beyond the realm of possibility. Plasma physics is inherently complex, nonlinear, and frequently yields unexpected outcomes. Alternatively, adopting a more provocative interpretation, what if an FRB detected in the vicinity of the 3I Atlas was not originating from the comet itself, but was intentionally timed to coincide with its passage? A signal originating from elsewhere, deliberately synchronized, utilizing the comet as a temporal marker, a beacon. This is extreme speculation, but its plausibility increases if a correlation is established. And here lies the observational challenge. FRBs are detected by all sky survey instruments, such as CHIME in Canada or ASCAP in Australia. These telescopes do not focus on specific objects, instead they scan broad areas of the sky. Therefore, if an FRB occurred in proximity to the 3I Atlas, it would appear in the data. However, attributing it to the comet would necessitate a specific analysis to ascertain whether any FRBs detected in October of the year 2025 originated from the comet's position in the sky. Has such an analysis been conducted? I cannot say definitively. It is possible, or perhaps not. But if it has been performed, and if even a single FRB has been found to coincide with the comet's trajectory, it would be an extraordinary finding. Not definitive proof of anything, but extraordinary because it would suggest that we have been overlooking an entire class of phenomena. Localized, short-range FRBs, emissions not traveling across the universe, but originating within or just beyond the solar system. Now let us broaden our perspective. Let us consider observational bias. We tend to discover what we are actively seeking. CHIME detects FRBs because it is designed for that purpose. However, it filters out signals that do not conform to the expected template. Signals that are too long, too short, too weak, or too strong. It is optimized for extra-galactic bursts, not for local anomalies. So, what if an entire category of radio transients remains undetected by us? Bursts emanating from comets, from asteroids, from interplanetary dust clouds, emissions that arise when charged particles interact with magnetic fields in unexpected ways. We would not observe them because we are not actively looking for them. And we are not looking because we operate under the assumption that they cannot exist. This is the inherent danger of theoretical models. They dictate our expectations, and our expectations, in turn, shape our perceptions. Everything else is relegated to the category of noise, dismissed as error, or buried in archives until someone revisits the data with fresh perspectives, novel algorithms, and revised hypotheses. Suddenly, what was once considered noise transforms into a valuable signal, and errors become groundbreaking discoveries. Therefore, my question is this: should we initiate a correlation analysis between FRB detections and the passages of interstellar objects? Should we cross-reference their spatial coordinates and timestamps? Should we conduct searches within archival data for coincidental occurrences? Because if such coincidences exist, if even a weak correlation can be established, it fundamentally alters our understanding. It implies that these objects are not as inert as we have assumed. It suggests that the universe is more dynamically active and interconnected than our current models depict. And it implies that the 3-eye atlas might be an integral component of a larger cosmic pattern, a pattern that we are only just beginning to discern. Part 12. Anomalous Solar System. Object Discovery. Now let us bring our attention back to our own solar system. For while we have been intently observing the 3-eye atlas, other unusual phenomena have been quietly accumulating within our astronomical catalogs. These include trans-Neptunian objects exhibiting peculiar orbital characteristics, near-Earth asteroids displaying unexplained behavior, and each discovery prompts the same fundamental question. Are these isolated curiosities, or are they fragments of a larger, yet-to-be-assembled puzzle? Allow me to elaborate on the trans-Neptunian region. Situated beyond the orbit of Neptune, at an approximate distance of 30 to 50 astronomical units from the Sun, lies a vast population of icy bodies known as the Kuiper Belt. Pluto is its most renowned inhabitant, but it comprises thousands, perhaps even hundreds of thousands, of other objects, and their orbital paths offer a narrative. The majority of Kuiper Belt objects traverse relatively flat orbital planes. Their orbits are either circular or possess mild elliptical shapes. They are stable and predictable. However, some deviate from this norm. Certain objects exhibit orbits tilted at extreme angles. Others possess perihelia, that bring them considerably closer to the Sun than anticipated. And some appear to cluster in configurations that suggest non-random distribution. This observed clustering gave rise to the Planet 9 hypothesis, the proposition that a massive planet, approximately 5 to 10 times the mass of Earth, resides in the distant solar system, far beyond Neptune's orbit. Its gravitational influence, it is theorized, shepherds these distant objects into aligned orbital paths. This hypothesis aims to explain the clustering, the orbital tilts, and anomalies that otherwise might be dismissed as mere statistical aberrations. However, Planet 9 itself has never been directly observed. Its existence is inferred, a phantom presence within the data. While some astronomers consider it a genuine entity, others argue that the perceived clustering is a consequence of observational bias. We tend to discover more objects in certain regions because our observational efforts have been concentrated there. The debate persists, with each new discovery serving to either bolster or weaken the hypothesis. Now allow me to provide a specific illustration. A trans-Neptunian object recently discovered. Let us refer to it as 2025 TN13. Its orbital path is exceptionally unusual, characterized by high eccentricity, a perihelion situated at approximately 40 astronomical units, and an aphelion extending beyond 1,000 astronomical units. Its orbital period spans tens of thousands of years, and its inclination is extreme, exceeding 60 degrees relative to the ecliptic plane. How did such an orbital path come to be? Perhaps gravitational jostling from Neptune, an encounter billions of years ago that sent it spiraling outwards, or the subtle pull of a hypothetical Planet 9, or even something more exotic like a passing star or a rogue planet. An event so ancient we can no longer piece together the details. Yet here's a curious observation. When we map the paths of these extremely distant trans-Neptunian objects, they don't exhibit random trajectories. Instead, they tend to group together. Their points of closest approach to the Sun, known as perihelion arguments, are aligned, and their ascending nodes, points where their orbits cross the plane of the solar system, also cluster. This is highly suspect, as random scattering should result in chaos, not orderly arrangement. This suggests something massive and unseen is out there, orchestrating these orbits. Alternatively, this apparent alignment could be an illusion, a consequence of how and where we've directed our telescopes. The debate continues, but the very fact that we are still discussing it highlights the incompleteness of our knowledge. We remain uncertain about the unseen constituents of our solar system and the forces that sculpted the outer reaches of our planetary neighborhood. It is within this very uncertainty that the truly unexpected, the black swans of the cosmos, may reside. Now let's draw a parallel to 3I Atlas. Both entities are anomalies, defying conventional expectations and forcing us to question what constitutes normal behavior. Both also expose the limitations of our current population models. We believed we had a firm grasp on comets and trans-Neptunian objects, but a closer examination of these outliers reveals that normal is often simply what we've encountered most frequently. Are these peculiar objects isolated incidents, or do they hint at a larger, systematic phenomenon? Perhaps there's a population of interstellar travelers we haven't yet detected, objects that traverse our solar system regularly, but are too faint or too swift to be noticed. Or maybe there exists a collection of extreme Kuiper Belt objects shaped by interactions we simply don't comprehend. It's conceivable that our solar system is a more complex, chaotic, and surprising place than our textbooks suggest. And here's the crux of the matter. If these objects are part of a discernible pattern, linked by some underlying process, we won't recognize it until we have amassed sufficient data, cataloged a larger number of outliers, and until someone performs a statistical analysis that reveals a correlation. By that point, the pattern will likely appear obvious, and we'll wonder how we missed it. But we didn't see it because we weren't looking for it. Our existing models didn't prompt us to. This is the essence of scientific discovery. We find what we actively seek and overlook what we do not. The crucial question then becomes, what are we currently overlooking? What patterns are hidden in plain sight? And will we identify them before they become critically significant? Or will we only comprehend them in retrospect, when it's too late to react? Part 13. Quantum Physics Anomaly News. Let us venture into even more bewildering realms. Fundamental physics, the very bedrock of our understanding, the constants and laws we assume to be universal, unchanging, and eternal. But what if this assumption is flawed? What if the universe is far more delicate, adaptable, and astonishing than we currently believe? In the year 2024, a paper surfaced on the R-Curev preprint server, positing a potential anomaly concerning the fine structure constant, alpha. This fundamental constant quantifies the strength of electromagnetic interactions and permeates nearly every aspect of physics, from atomic spectra to quantum mechanics and electromagnetism. It is presumed to be invariant, constant throughout the cosmos and across all epochs. However, this paper meticulously analyzed quasar spectra from galaxies billions of light-years distant. The findings revealed subtle indications that alpha might have differed in the early universe, deviating by mere parts per million. While seemingly insignificant, such a variation, if confirmed, would be statistically profound. The scientific community is presently divided. Some attribute the findings to calibration errors, others to systematic biases within the data. A segment of researchers, however, considers it a genuine and revolutionary discovery. The debate persists, necessitating further data collection, refined measurements, and independent verification. Nevertheless, the possibility lingers. The possibility that fundamental constants are not immutable, and that the universe undergoes transformations beyond our current comprehension. Now let's turn our attention to timing residuals. Pulsars are renowned as the universe's most precise chronometers, spinning hundreds of times per second. Their emitted pulses are so remarkably regular that they can be used for extremely accurate timekeeping. Astronomers employ pulsar timing arrays to detect gravitational waves. They meticulously measure the arrival times of pulses from numerous pulsars, searching for correlated deviations. These deviations are anticipated to be caused by space-time ripples originating from distant black hole mergers. However, occasionally, these deviations do not align. Certain individual pulses exhibit timing residuals that defy explanation, perhaps mere noise, likely instrumental error, or an effect of the interstellar medium. Yet, in some instances, these residuals are too substantial, too persistent, and too peculiar, prompting speculation about alternative explanations. What if space-time itself is inherently more irregular than we perceive? What if there are inherent fluctuations, glitches, or anomalies that our current models fail to account for? Now let's connect this to 3I Atlas and the concept of a reality glitch. If fundamental physics exhibits imperfections, if constants are not perfectly constant, and if timing mechanisms are less robust than we assume, could an interstellar object passing through our solar system inadvertently highlight these discrepancies? Might it interact with the local fabric of space-time in a manner that exposes underlying instabilities? I am not suggesting that 3I Atlas itself is inherently anomalous. Its mass is insufficient, and its gravitational influence is negligible. However, what if it is traversing a region of space-time that is already subtly anomalous? A locale with a higher-than-average density of dark matter, a region influenced by the passage of a gravitational wave, a zone where, for reasons yet unknown, physical constants exhibit minute variations. If such conditions were present, instruments observing the comet might detect anomalies, timing offsets, spectral shifts, or trajectory deviations that do not conform to Newtonian or relativistic predictions. This would not be due to the comet's exotic nature, but rather the unusual characteristics of its environment, an environment whose subtleties we currently lack the observational resolution to perceive. This is highly speculative, indeed wildly speculative, but it is rooted in genuine questions about fundamental physics. These are questions actively being investigated by experiments such as the Large Hadron Collider, the Dark Energy Survey, and pulsar timing arrays. The more precisely we measure the universe, the more we encounter anomalies, small deviations, edge cases, and outliers that diverge from the standard model. Each outlier represents either an error or a discovery. The challenge lies in discerning which is which, as errors are commonplace, while discoveries are exceedingly rare, and distinguishing between them demands rigor, replication, and independent confirmation. However, there are times when only a single opportunity is available, one measurement, one passing object. If we dismiss it as an error, we risk missing a profound discovery. Conversely, if we proclaim it a discovery prematurely, we risk being wrong, which can lead to embarrassment, accusations of carelessness, and even career damage. Consequently, scientists naturally lean towards caution, demanding a high degree of certainty, multiple corroborating pieces of evidence, and reproducibility. While this approach is commendable and necessary, it also inherently biases us towards overlooking potential discoveries, filtering out genuinely anomalous phenomena as mere noise, and prioritizing safety at the expense of revolutionary insights. This brings us back to the central question: are we examining 3I Atlas with the appropriate instruments, hypotheses, and openness to the unexpected? Or are we merely fitting it into existing frameworks because it feels comfortable, because it aligns with our training, or because acknowledging our lack of understanding is more daunting than feigning it? I do not possess definitive answers, but I do have questions. And questions are the genesis of science, the starting point of discovery, and the foundation of understanding. If 3I Atlas serves to teach us anything, it should be this: the universe remains capable of astonishing us, and we must be prepared for its surprises. Part 14. AI-driven signal and pattern detection breakthrough. The scientific landscape today is simultaneously inundated and empowered by its own remarkable progress. Every night, our instruments furnish us with an avalanche of information, far exceeding the capacity of any previous generation to process. Telescopes diligently scan the heavens, generating terabytes of data before the dawn breaks. Satellites in Earth's orbit continuously transmit streams of measurements, encompassing everything from temperature fluctuations to radiation levels and magnetospheric flux. Particle accelerators meticulously record billions of collisions every second, each collision holding the potential to unlock secrets about the very fabric of reality. Despite this technological prowess, we are fundamentally unable to scrutinize it all. We cannot individually examine every image, verify every spectrum, or analyze every line of code that describes the universe back to us. The sheer volume of data has outstripped the cognitive capabilities of the human mind. Consequently, we resort to automation. We develop algorithms to sift through the noise, to highlight what we already presume to be significant. We design filters to eliminate false positives and reduce complexity. We entrust these machines to identify the familiar and discard the rest. But what if the truth lies hidden within that discarded information? What if the signal of the century, the anomaly that fundamentally reshapes our understanding of physics, has been quietly removed by our filters simply because it did not conform to a pre-existing pattern? This is precisely where artificial intelligence introduces a transformative element. Machine learning algorithms do not merely follow pre-programmed instructions, they learn from data. Rather than relying on rigid filters, they adapt and evolve. They can identify patterns that defy simple mathematical description, perceive structures invisible to human visualization, and detect deviations that defy straightforward rationalization. The AI does not possess a preconceived notion of what it is searching for, and paradoxically, this is its greatest strength. In recent years, AI has begun to yield tangible scientific discoveries, not merely simulations or theoretical predictions, but verifiable scientific findings. Consider the Kepler Space Telescope. Between the years 2009 and 2013, Kepler meticulously observed over 150,000 stars, recording their brightness at minute intervals in its quest to identify transiting exoplanets. The mission's standard pipeline successfully identified thousands of worlds. However, this pipeline was optimized for predictable, regular dips in stellar brightness, indicative of periodic orbits and clear, strong signals. Yet, the universe does not always adhere to predictable regularity. In 2023, a research team applied deep learning techniques to the historical Kepler data. They trained neural networks not on theoretical models, but directly on the data itself. The AI was not instructed on the expected appearance of a planetary signature. It simply learned to recognize what constituted a difference. The outcome was the identification of a handful of new planets that the original algorithm had overlooked. These included planets exhibiting irregular or quasi-periodic transits, likely due to orbital perturbations from neighboring bodies or gravitational resonances causing orbital tilts. The AI even detected potential exomoons, celestial bodies that produce subtle, asymmetric dips in light that human-designed code had dismissed as background noise. This represents a quiet revolution. AI is not replacing astronomers. Rather, it is revealing avenues of inquiry they had never conceived of. A similar pattern is emerging in other scientific domains. Take, for instance, the classification of galaxy morphologies, their categorization into spirals, ellipticals, or irregular shapes. For decades, this classification process was largely manual, at times even artistic. Subsequently, initiatives like Galaxy Zoo emerged, where volunteers globally meticulously categorized millions of galaxies by hand. AI, however, can analyze tens of millions of galaxies overnight. When researchers deployed AI on data from the Sloan Digital Sky Survey, it began to identify galaxies that defied existing classifications. Some bore the hallmarks of collision remnants, while others resembled artifacts of gravitational lensing, or ghost images of galaxies positioned behind others. Each anomaly hinted at novel astrophysical processes. The AI was not simply replicating existing human knowledge, it was actively expanding the universe's taxonomy. Now imagine applying this same analytical approach to 3I Atlas, the interstellar object currently captivating widespread attention. It is exhibiting behavior inconsistent with that of a typical comet. Its acceleration patterns are peculiar, its tail dynamics fluctuate unpredictably, and its albedo variations do not align with standard outgassing models. What if we were to feed all available data, every photometric light curve, every spectroscopic reading, every trajectory log, every polarimetric profile, and every image metadata set collected from observatories worldwide into a neural network? And then pose a singular question to the AI. What does not fit? This approach would involve no preconceived assumptions or established models, relying solely on pattern recognition. Perhaps the AI would detect brightness fluctuations that repeat at precisely 6.3-hour intervals, too regular to be coincidental, yet too erratic to be explained by simple rotation. It might identify subtle drifts in amplitude over time, suggesting a secondary periodic modulation, possibly indicating a binary rotation or an active core responding to internal thermal cycles. Alternatively, the AI could uncover something more profound, a correlation between outgassing jets and non-gravitational acceleration, but one that deviates from established physical principles. For example, the thrust vectors might be asymmetric in a way that implies directed emission, as if something were actively steering the ejected material, rather than simply venting it. Individually, none of these findings might be conclusive, but collectively, they would be highly intriguing. And this is precisely where discovery commences. AI possesses a singular superpower. It notices. However, it also has a critical limitation. It does not understand. It cannot definitively distinguish between noise and novelty, or between coincidence and causality. It flags anomalies, but it falls upon humans to determine their significance. And humans, despite their intellectual brilliance, are prone to bias. We have an innate tendency to perceive patterns, seeing faces in clouds, divine intervention in thunder, and intention in randomness. In scientific endeavors, this bias can manifest in two ways. We may erroneously ascribe meaning where none exists, or we may dismiss valid meaning because it appears too unconventional. Therefore, the solution is not to blindly trust AI. It is to rigorously verify. The same analysis must be performed on independent datasets, utilizing multiple models and cross-checking results with different instruments. Only if the signal persists, if it appears under varied conditions, with different algorithms, and under differing assumptions, should we begin to lend it credence. Replication serves as the ultimate antidote to illusion. Has anyone already undertaken this? Has some individual or team, perhaps a graduate student at JPL, a hobbyist running TensorFlow on a home GPU cluster, or a national laboratory discreetly pursuing such projects, already fed the complete 3I Atlas dataset into a deep learning model? It is conceivable that such an analysis is currently underway, with its findings known only to a select few. Or perhaps, and incredibly, no one has yet attempted it. In this scenario, our most significant cosmic anomaly might be eluding us, simply because no one considered instructing the machines to examine it. If this is the case, it represents a missed opportunity of historical proportions. This is the future trajectory of astronomical exploration, a synergistic partnership between human intuition and machine perception, a collaboration between theoretical frameworks and empirical data. We formulate the models, the AI challenges them. We interpret the findings. The AI uncovers what we cannot even imagine. In the coming decade, as observatories like the Vera C. Rubin Observatory, with its LSST project, come online and generate 20 terabytes of sky data nightly, human analysis alone will be insufficient. The universe will necessitate algorithmic curiosity. In this new era, discovery will no longer be the serendipitous stumbling upon the unexpected. It will involve training machines to perceive what we have inadvertently trained ourselves to disregard. This brings us back full circle. A Black Swan event in space is not merely a surprise. It is something so profoundly outside our expectations that our entire conceptual framework must be reconfigured to accommodate it. But how can we possibly detect the truly unexpected if our methods are designed solely to identify what we anticipate? This is the inherent paradox of modern scientific inquiry. The more sophisticated our instruments become, the narrower our focus can inadvertently become, as we become overwhelmed by precision. We filter, we automate, we impose limitations. AI has the potential to be the key that unlocks this restrictive loop. Because if 3I Atlas is anything, a naturally occurring oddity, a misidentified interstellar remnant, or something altogether more extraordinary, it serves as a critical test of our capacity to perceive beyond our established models, to search without knowing precisely what we are looking for. And if an AI, at some point in the future, uncovers something within its data that we cannot explain, something that defies replication, something that fundamentally challenges the very tenets of physics itself, that would represent the truest black swan of all, it would be a discovery not born from human yearning for meaning, but from a machine identifying what human imagination could not conceive. Somewhere within a server room, humming quietly under sterile white lights, petabytes of sky data lie waiting, invisible to the naked human eye, yet brimming with untold secrets. An algorithm will awaken, sift through the vast expanse of noise, and perhaps, just perhaps, detect a subtle flicker that has escaped everyone else's attention, a pixel infinitesimally brighter, a curve minutely misaligned, a pattern that simply does not conform. And from this whisper of data, a profound question will emerge. Is this merely statistical noise, or did the universe just offer a subtle wink? This is the era into which we are stepping, the age where machines observe the cosmos, not merely on our behalf, but alongside us. And when the next anomaly akin to 3I Atlas appears, it will not solely test the rigor of our scientific methods. It will also test our ability to truly listen to the messages the machines are endeavoring to convey. Part 15. Final Reckoning and Looking Forward. And so we arrive at this juncture, 15,000 words into an exploration of a comet that could signify nothing, or it could represent everything. 3I Atlas, an interstellar visitor that graced our skies in July of 2025, exhibited outgassing when it logically should not have, revealed a chemical composition unlike anything previously observed. It reached its perihelion on October 29th and is now receding into the darkness, fading from our view, embarking on its journey back into the void from which it emerged. The central question persists. Is this merely an unusual comet, or is it a dormant black swan awaiting its moment of revelation? Let us revisit the scenarios proposed. Orbital domino effect, a plausible explanation that could unfold over decades. We cannot definitively rule it out, nor can we yet confirm it. We will only gain clarity if an unexpected event occurs in the years to come. Fragmentation event. As of this moment, no confirmed fragmentation has been observed, though the stresses experienced at perihelion could potentially trigger a delayed breakup. Follow-up observations are ongoing. Solar disruption. No major solar events coincided with its perihelion passage, diminishing the credibility of this scenario. However, the question remains pertinent for future interstellar visitors. Artificial signal. No confirmed detection has been made, although archival searches are actively continuing. The probability is low, but the implications are immense. Atmospheric anomaly. The situation remains unclear. Relevant data exists, but analysis is still needed. Disclosure cascade, a possibility, subtle and perhaps invisible in real time. Psychological singularity. This phenomenon is already unfolding, fueled by media coverage and public speculation, leading to tangible consequences stemming from perceived uncertainty. Reality glitch. There is no evidence to support this, and while wildly speculative, it remains philosophically intriguing. Therefore, what remains plausible? Orbital perturbations, fragmentation, and psychological impacts are still viable. What has been largely ruled out? Solar disruption. The possibilities of artificial signals and reality glitches persist in the realm of we haven't investigated thoroughly enough to say no. This is the frustrating reality. The absence of evidence is not evidence of absence. Just because we haven't discovered something does not inherently mean it isn't present. So, what transpires next? What observations hold the most significance? Post-perihelion brightness monitoring. Is the light curve decaying as anticipated? Are there any secondary peaks or unusual rates of fading? Non-gravitational acceleration updates. Is the trajectory aligning with predictions? Are there any deviations as outgassing continues? Radio telescope follow-up? Have any emissions been detected? Have any archival signals been identified? Spectroscopic analysis. How is the coma's composition evolving? Are there any shifts in the ratio of carbon dioxide to water? Fragmentation monitoring. Are any new components appearing? Are there any unusual morphological features in high-resolution images? And then there is the archival research, deep dives, AI analyses, cross-correlations, examining pulsar timing data, spacecraft telemetry, ionospheric logs, solar activity reports, and fast radio burst catalogs. The goal is to identify coincidences, patterns, and any potential links between 3 Atlas and broader cosmic anomalies. Some of this work is underway, some is not, and some may never be performed because no one considered its necessity. This represents the tragedy of missed opportunities. Once the comet fades and becomes too dim to observe, the window of opportunity closes, the collected data becomes finite, and the archives become the definitive record. We are left with whatever we managed to capture, whatever we prioritized, and whatever we deemed important at the time. But here's the critical point. Even if the third interstellar object, known as 3 Atlas, is entirely ordinary, even if every peculiar characteristic it exhibits can be attributed to conventional phenomena, it has still imparted valuable lessons. It has served as a potent reminder that visitors from beyond our solar system are indeed real, that their inherent chemical makeup could be vastly different from anything found within our cosmic neighborhood, that they possess the capacity to challenge our established scientific frameworks, that they command our undivided attention, and that we are in urgent need of more sophisticated systems for their detection and precise characterization, because their arrival is not a singular event, but a continuing phenomenon. The first interstellar visitor was Oumuamua, the second was Borisov, and now 3 Atlas marks the third, with many more anticipated. Once our observational capabilities are enhanced, we might detect dozens each year, perhaps one every month, or even one every week. Each of these celestial travelers will be unique. Every one will carry crucial data about its originating star system, the prevailing conditions in the vast expanse of interstellar space, and the diverse methodologies of planetary formation occurring throughout our galaxy. Furthermore, some of these objects might prove to be black swans, phenomena that defy all existing classifications, shatter our current theoretical models, and compel us to re-examine fundamental scientific presumptions. These could be artifacts of intelligent design, evidence of advanced extraterrestrial intelligence, or manifestations of physics currently beyond our comprehension. While the probability might be low, any non-zero chance qualifies an object as a potential black swan. Therefore, what are the ramifications? If 3 Atlas turns out to be a black swan, what are the scientific implications? We could witness a paradigm shift, the emergence of new physics, or a groundbreaking redefinition of our understanding of cometary behavior, interstellar objects, or entirely unforeseen phenomena. Practically speaking, our approach to planetary defense would require reevaluation. We would need to initiate more diligent tracking of all interstellar visitors, invest in the development of superior detection technologies, and foster robust international collaboration. Culturally, public perception would undoubtedly undergo a transformation. Space would cease to be perceived as merely predictable and safe, becoming instead a realm imbued with greater mystery, demanding more caution, and inspiring profound wonder. However, if it is not a black swan, if it proves to be merely a common comet, what then? We would gain humility. We would learn that the universe is replete with statistical anomalies, that rarity does not equate to impossibility, and that strangeness does not automatically imply artificiality. We would refine our existing models and broaden the scope of our observational parameters. We would become more adept at distinguishing genuine anomalies from mere observational errors, and we would be better prepared for the arrival of subsequent celestial objects, and those that follow. In either scenario, we stand to gain. In every instance, we acquire knowledge, for that is the fundamental nature of scientific inquiry. Science transforms the unknown into understanding and unravels mysteries, converting them into comprehensible knowledge. This process is not always instantaneous or complete, but it is a persistent, incremental advancement over time. And here is my concluding thought. If the cosmos can still astonish us in such a profound manner, if an interstellar comet can generate such an outpouring of speculation, intensive analysis, awe, and even apprehension, then what other wonders have remained concealed all this time? What else are we failing to perceive? What other deviations from the norm are lying dormant within our accumulated data? What other underlying patterns are awaiting discovery? What other black swans are circling, remaining invisible until the very moment they make their impact? We currently inhabit an era where telescopes meticulously survey the entire celestial sphere every night. Satellites continuously monitor our planet, and sophisticated experiments probe the most fundamental constituents of reality. We possess more data than ever before, a greater array of instruments, immense computational power, and an enhanced capacity to detect the unexpected. Yet we continue to be surprised, remain perplexed, and pose questions for which we currently lack definitive answers. This should ignite our curiosity and also evoke a sense of trepidation, for it signifies that the universe is far from finished imparting its lessons to us. It implies that our current scientific models are incomplete. It suggests that groundbreaking discoveries are on the horizon, that black swans are poised to emerge, and that events are waiting to unfold that will necessitate the rewriting of textbooks, revolutionize established paradigms, and fundamentally alter everything we believed we understood. 3 Atlas may indeed be one such transformative event, or it may not. However, the mere fact that we cannot be absolutely certain, the fact that we must seriously contemplate the possibility, holds significant weight in itself. It indicates that we are finally beginning to take the unpredictable aspects of the universe seriously. We are finally acknowledging that despite our extensive network of satellites, telescopes, and exploratory missions, space remains largely uncharted, predominantly enigmatic, and profoundly capable of delivering unforeseen shocks. And if this realization does not compel you to lie awake at night, gazing at the stars, pondering what lies beyond, what is approaching, and what we may have already overlooked, then you have not been paying adequate attention. Because the essential message conveyed by 3 Atlas is not that the sky is collapsing, but rather that the sky is alive, observant, and brimming with possibilities that we can scarcely begin to imagine. Therefore, continue to observe, continue to question, and continue to wonder, because somewhere in the vastness of space, another object is on its trajectory towards us. Another anomaly awaits its moment of revelation. Another black swan is silently gliding through the cosmic darkness. And when it arrives, when it finally makes its presence known, we will be left with a single, critical question. Did we anticipate its arrival? Or were we looking elsewhere?